Okay, good morning everyone. Let's get started. You are working on your third milestone. Hopefully you've gotten into the rhythm now of taking weekly bite-sized chunks in approach to your final project. Just a couple reminders. I've said this a couple times, but maybe worth repeating. I've noticed in a lot of office hours, folks are still confused about the fact that your experimental platform is actually operating at two different time scales. We have evolutionary time measured in the number of generations. So in generation 0, you're evaluating n random parents. If you're using the parallel hill climber, that's generation 1. Generation 2, you're evaluating each of those parents' children, deciding whether the child or parent survives, moving on to generation 3, 4, 5, 6, 7, and so on, right? That's evolutionary time. That's the slower time scale. Over that evolutionary time scale, you should be seeing fitness increasing or decreasing depending on whatever the problem is that you're trying to solve. Ultimately, at the end of the semester, when you present your final project, what we would like to see is a couple of videos from here, from generation 1, from random parents. You've got a quadruped that dances around on a runway and then falls off. We see a second parent stand still and not do much of anything, right? So typical random behavior for your robot in its environment, whatever that environment is. Then we would like to see some videos of evolved parents that exist at this point in time. Not children, because the children at this generation may be no more fit than the parents at this generation. Why? Take the parents that you have here, they produce children, and you generate videos from that, and they don't look much different from the parents over here. Well, why not? Most likely.
Those children are still just randomly mutated and
They're randomly mutated, right? We take a very optimized machine like my laptop here, and we go in and randomly rearrange some circuitry. Possibly that new machine is not going to perform any better than a dead laptop, right? What we want to see is parents from here, and ideally the most fit parents from this population. And if we see 2 videos from here and 2 videos from here, within about 5 or 6 seconds, we, meaning myself and the TA, probably anyone in this class at this point, would be able to immediately see a difference. We see a quadruped that takes 4 or 5 or 6 or 9 steps straight down a relatively narrow runway, or takes 3 steps up a flight of stairs, maybe not 4, maybe doesn't get to the top of the stairs, but there is a clear difference. You're going to try and demonstrate provide video evidence to us at the end of the semester that evolution occurred. Whatever your robot is, whatever the environment is, whatever the fitness function is, whatever the neural network controller is for that robot, evolution has been able to take some random stuff and turn it into something that does something that's obviously non-random. Yeah. Even if we, the TA, don't see what the fitness function is, we don't know what the neural details of the neural network controller in your robot is, we should be able to see a difference. Yeah. That's the main thing we are looking for, and you should be looking for, especially heading into milestone 4 and then the final project itself. So far, so good? Okay, so that's the slower time scale, and then within any one generation, there is the faster time scale, which is the individual time steps that elapse. I'll put T for time here. The individual time steps that elapse in the simulation itself, an individual simulation of an individual parent or a child. Yeah. This can be a little bit confusing when you're trying to explain to yourself and explain to us. Here you can see this change happening over simulation time. Here you can see the robot lifting up, grabbing onto the rung of a ladder and pulling itself up onto the rung. It's perfectly fine, but we're talking about this time scale. We can simultaneously talk about this time scale. As you see, comparing these 2 videos to these 2 videos, my robot is now evolving the ability to reach up and pull itself up on the first 2 rungs of a ladder. and then fall off. No better, but at least clearly progress. Yeah? Okay, any questions about any of that? Okay. One other thing I want to just reiterate, and I apologize, I've said this a couple times before. Several students have asked about how to save the state of your evolutionary algorithm. We don't all have a whiz-bang laptop. You're going to exert a fair bit of computational pressure on your machine over the next few weeks. As I mentioned, ideally it would be great if you could run things overnight and play back the best you get in the morning, but some of your laptops might not survive the night. Some of you might need to run things in shorter periods, an hour, half an hour, 5 minutes. If you need to do that, as I mentioned before, familiarize yourself with the Pickle Python package. The Pickle package will take any data structure you like in your Python code and pickle it and save it in a file. You don't need to worry about all the nitty-gritty details of how to save it to a file. Pickle will take care of that for you. And then Pickle will also let you read in a data structure from a file. If you're going to save the state of your overall evolutionary run, you get to generation 6 and you want to save things out and then go to class and come back after class and continue at generation 7, what is it that you want to pickle? You could, for example, choose to pickle the brains of all of the parents at generation 6, but you're going to miss something, right? You're going to lose some other state of the robot. You could pickle your entire code base. What seems like the most likely target for the thing you want to save out to disk and then read back in? If you pickle the whole thing and read it back in, you'll be reading in your entire parallel hill climber.
Mostly need your neural net weights.
You need your neural network weights, which is fine for most of you, assuming that in your final project you're not also evolving the lengths of the legs, or the size of the stairs, or the distance of the target object that the robot is trying to get to. Ideally, in most cases, it's exactly that. But you might need to broaden what pickles to a file, depending on what you're doing. Yeah. So there is no one right answer to this. You could, for example, pickle and save the entire parallel hill climber. So it's one call to pickle, and it'll send the entire parallel hill climber, which includes every parent and the brain of every parent. And then you can read that back in and continue your parallel hill climber from that point. Yeah. Okay. Okay, I think that's all I had to share about the final project. Any questions? So far, so good? Okay, all right, so you're working on milestone 3. You're going to start in on milestone 4 next Tuesday, where you're going to start to develop some preliminary evidence for your A/B testing. I'll talk about A/B testing again on Tuesday morning just to reorient you for next week. Okay, back to lecture material. So we're working our way through open challenges in the field. We talked about trying to map good genotypes to phenotypes, and we've been spending the last 2 weeks trying to cross the reality gap, sprinkle noise on the simulator, use 3D printers to throw as many robots across the gap as you can. My contribution to this problem, the resilient machines problem, evolve simulators to more and more closely match reality and in effect narrow the gap. And we'll finish off lecture 17. We'll finish off lecture 17 this morning, which is the transferability project in simulation. Let's evolve simulators to produce the behavior we want and to produce transferable behaviors. Okay, so back to lecture 17. We spent the last part of last time talking about the particular evolutionary algorithm that is used in the transferability project, which is multi-objective optimization. We're going to be evolving a population of controllers represented here by dots, and the position of each dot represents how well that controller causes the simulated robot to exhibit the behavior we want, and how likely that behavior is to transfer to reality, which we haven't talked about yet. We ended by looking at some real data here. In this case, we've got on the vertical axis how well that controller causes the robot to do in simulation, where higher is better. Higher is further, higher is better. And on the horizontal axis here, they're still plotting transferability, but they're plotting it slightly differently. They're computing transferability as the approximated sim to real disparity. How much different is the behavior produced by this controller, for example, going to be on the simulated robot compared to the real robot? We're trying to minimize this metric, this fitness objective, and we're trying to maximize this fitness objective. So we're trying to push the Pareto front, represented by the black dots. We're trying to push that up and to the left. This was the state of an evolving population at a given generation, generation I, so in this long time scale. And then this is what things looked like one time step, now I'm confusing time scales. One generation later. We can see generally things are moving up and to the left. Okay, now everybody good with multi-objective optimization? Let's talk about transferability. Okay, so we went through this sort of question and answer back and forth at the beginning of this lecture, and we got stuck on the following problem. If we want to compute the transferability of every controller in simulation before we get to reality, how are we going to do it? The simplest thing is measure transferability in sim and real, but then we'd have to evaluate every controller on the real robot. There'd be no point to simulation to begin with. So it seems like there's kind of a chicken and the egg type problem here. Here's how these authors solved this chicken and egg problem. Let's do this using this geometric interpretation that we can use from multi-objective optimization. We've got transferability on the horizontal axis. I don't know about you, but it's always easier for me when I think about multi-objective optimization for all the objectives to either be maximized or minimized. I don't like when people mix up, I've got to maximize this thing and minimize, I can't, it's too much for my puny human brain. So we're going to go back to maximize objective 1 and maximize objective 2. Okay, let's run a hypothetical multi-objective optimization run. We're going to create a population of random controllers, like we always do, sets of synaptic weights. We're going to take each set of synaptic weights, download it onto the simulated robot, let the simulated robot do its thing, and now we have one of the two numbers for each controller. We know how good the behavior is of the simulated robot when it's running that controller. We do not know the second number, how transferable that random controller is if we were to send it to reality. So using the geometric interpretation of multi-objective optimization, we can take all of the points, which represent all the random controllers, and collapse them onto one vertical line. As far as we know, transferability is unknown. Okay, we've evaluated all n random controllers in simulation, and now we're going to pick one and send it to reality to compute that one random controller's actual transferability. Which one do you want to pick? You can pick any one you want. We've got all these dozen or so controllers sitting on this vertical line. Which one shall we send? You're all expert roboticists now. You can rely on your intuition. Which one?
I would pick one in the middle.
One in the middle. Why the middle?
Well, we said earlier at the bottom that like a robot that just sits there will transfer really well, so we don't want to pick anything whose behavior was really poor. And then on the flip side, robots whose behavior was really good in sim might be exploiting the sim or relying on some unrealistic aspects.
Good point, right? So probably better to err on the side of caution and choose a middle road. As you just said, controllers down here that cause the robot not to move in simulation, very likely to also not cause the physical robot to move. We can probably be relatively confident in what the transferability is of these points that are low down in the graph. Similarly, like you said, the ones that cause the robot to really shuck and jive in simulation, probably they're going to be exploiting some aspect of the simulator, or they're being overly optimistic about the strength of the motors. Those are probably not going to transfer very well, but we're kind of uncertain about the ones in the middle. So if I were running this experiment, I'd probably do what you said, which is go with the middle. These authors were quite optimistic, and they took the best one and sort of crossed their fingers. Yeah? So let's say we pick this one, the one that causes we pick the controller that causes the simulated robot to move as far as possible in simulation. Here we go. Here it is. This is not actually a random controller, as you can probably guess. This is a few seconds on in evolution in simulation. So they did a little bit of evolution with just one objective. Let's transfer it to reality. What a surprise. Evolution has started to exploit whatever detail, whatever inaccuracies and errors exist in this simulation, and it didn't transfer well to reality. Okay, so we failed to cross the gap, but the transferability experiment as a whole has not failed because we've learned something. We now know that this controller up here has very good behavior and very low transferability. Okay, so we've learned something. Now you get to send a second one to reality. Which one are you going to send? You'd hope that these authors have learned their lesson at this point, right? What kind of intuitions do you have at this point? As always, we don't want to send all of them. If we send all of them, then we don't really need simulation, right? We're trying to be as smart as we can. We're trying to send ones that are likely to produce the desired behavior we want in reality without having to send all of them. What do we pick next? Still feeling optimistic? Shall we send this one? Good. Okay. I see you all shaking your heads. Actually, at this point, there's two good reasons to not send this one. The first one, which you already mentioned, it's probably exploiting aspects of the simulation. The fact that these two individuals are so close to one another in terms of the kind of behavior they produce in the robot, those controllers themselves are probably similar. They might be siblings or first cousins or second cousins, depending on the evolutionary algorithm. They're probably related. So if one of them failed to cross the gap, its relative is also probably likely to not cross the gap as well. So we're actually going to try and pick a controller that is quote unquote distant from the one that we already sent across the gap, because the similar ones that are quote unquote close, and we'll define close and far in a moment, but intuitively, hopefully you can already see what we mean by distance here. Controllers that are close, we can be kind of confident in their transferability metric. So I've drawn these two dots here that are close on the transferability axis to indicate we can probably make a pretty good guess about how they're going to transfer. And we can also probably be pretty confident in ones way down here. These ones are probably over here. The ones in the middle now, the ones that are far, controllers that are far from the ones that have already crossed the gap, we're going to have high uncertainty about their transferability. So we can actually quantify for all the controllers in the population that we have not yet sent to reality, we can quantify the amount of uncertainty we have about their transferability values, and we choose the one for which we have most uncertainty. Yeah? This paper was published 4 years after our Resilient Machines project, which we talked about last time. And in that project, you saw we were also relying on uncertainty. The physical robot was carrying out actions about which it was most uncertain. Similar idea here. This actually crops up in a lot of places in robotics and biology, and it's known as infotaxis. So taxis behavior means any behavior where the organism or the machine is trying to go towards or run away from light, heat, predator, prey, potential mate. If you think back to the beginning of the semester, where did we see simple robots exhibiting taxis behavior? The Bradenberg vehicles, right? Those were exemplars of taxis. You can taxis for concrete things like heat and light and love and all sorts of things. You can also chase after information, right? I can do things about which I'm maximally uncertain. Toddlers love to exhibit infotaxis. Let's see what happens if I go off the top of the stairs at home. Teenagers also like to do infotaxis. I'm going to borrow the car under these conditions, and let's see what mom and dad think about that. Yeah? Lots of examples of organisms and machines where sometimes it makes sense to chase after information. Here is yet another example of it. This algorithm itself is going to send controllers to reality, most likely to bring back new information about the real world. In this case, that particular information is how well or how poorly do different controllers transfer to reality given the robot that they're running on. So far, so good? Questions? Okay. All right. So the solution to this problem of transferability that the investigators reported in this paper is to estimate transferability of a controller based on that controller's behavioral similarity to a tested controller. A tested controller is going to refer to controllers we've already sent across the gap. So what does it mean for controller I and controller J? What is behavioral similarity between them mean? It means we run controller I on the simulated robot, run controller J on the same simulated robot, and then compare the behaviors, those two behaviors resulting. The more similar that behavior, the more similar the controllers. Why didn't they just simply take the distance between the controllers themselves? Remember that a controller is a vector of floats. It's a set of synaptic weights. So controller I and controller J, they have a relatively obvious way to compute distance between them. Take the Euclidean distance between the synaptic weights in controller I and controller J. Why don't we define distance that way? Let's imagine controller I. We run it on the simulated robot, then we send controller I across the gap, and we run controller I on the real robot, and it doesn't transfer very well at all. We find another controller J in the population that has very, very similar synaptic weights. They're almost identical, but not quite the same. And if we were just to directly compute distance between controllers as the distance between their synaptic weights, we might conclude that controller I and J are close in synaptic weight space. So therefore, controller J is probably also not going to cross the gap very well. That's not what they're doing here. Why not? What's the problem with that? It's easy. It's an obvious way to compute distance. It's not what they did.
For one, we have these incredibly noisy, like loss landscapes and gradients, so a small change in that vector space could potentially yield a very different result in behavior.
Absolutely.
That's kind of what we're trying to capture. So
that's what we care about. We don't care about the actual synaptic weights of the controller. What we care about is what does the controller make the robot do, right? You might have seen this when you're running Evolution now on your own local device. Sometimes you see a parent that's got a beautiful, clean, relatively clean gait. It produces a child which has one slightly different synapse, and that child doesn't move at all or moves completely different from the parent. So you can have two different controllers which are genotypically close. Remember, genotype is the set of synaptic weights, but phenotypically very different. Same thing happens in nature. Sometimes there are mutations that result in a child so that the child's and parents' genomes are almost identical, but whatever that mutation is, it causes a huge change in the child, and the child barely resembles the parent. Happens all the time. Okay, so behavioral similarity. But now, as always in science, we've solved one problem, and now we have 10 more problems, or at least 10 more questions. If we're going to measure the distance between controller I and J by the differences in behaviors produced by I and J, how do we measure the similarity between behaviors? Ideas?
By the difference in fitness function, maybe?
Makes sense, right? The simplest thing is, what's the difference in fitness, right? Okay, so let's say we have controller I and J, and controller I causes a quadruped to stand up and exhibit a beautiful, upright, legged, locomotory gait. Controller J produces sliding and crawling in exactly the same quadruped, and they both get almost the same fitness value. They travel almost the same distance, but do so in very, very different ways. According to that behavioral similarity metric, which we're going to base on fitness, is that a good measure or not? Probably not, because
they're moving in completely different ways but achieving the same fitness.
But why does it matter that they're moving in different ways?
Well, because we want them to be doing different things to see if they can cross the reality gap.
If one of those does or doesn't cross the gap, that says absolutely nothing about whether the other one might cross the gap or not. And we're trying to define a behavioral similarity metric so that controllers that have similar metrics, similar distance metrics, transfer similarly. So good idea, it would be the simplest thing to do, but it is also flawed. So computing the distance between two controllers based on genotype doesn't work for the reasons we mentioned. Comparing controllers based on fitness outcomes also doesn't work for the reason that we mentioned. It's the way in which the robot moves as a result of the controller that's going to make all the difference in whether or not it transfers from simulation to reality. So in this paper, as we're going to see in a moment, they define a behavioral similarity metric that's based on the way the robot moves when running a controller. Everybody see the intuition? Okay. All right. So here we go. Sorry about my red box here. It seems to be off-center. We're going to define a distance measure based on any two behaviors in terms of how those behaviors actually play out. So we're going to define a vector B, and this vector is going to be associated with every controller. So if we have controller I, it produces vector BI. And vector B, in this case, contains 3 elements. It could be n elements, where every element in the vector represents some feature of the behavior of the robot when it's running that controller. In this case, the authors kind of arbitrarily chose 3 features of behavior that, when you read them off, kind of make sense. You can kind of expect that those features affect whether or not a controller will transfer to reality. You don't know how it will affect how the controller will transfer to reality, but they probably will have an effect. For example, as you mentioned, fitness, just the actual distance the robot travels, that actually does say something about whether it's going to transfer from sim to real. If F1, feature 1, is 0, the robot doesn't go anywhere, yeah, it's probably going to transfer well to reality. But if F1 is non-zero, the robot traveled 2 meters forward, Again, it depends. It's not enough. It's useful, so let's throw in some other features as well. F2, they picked the mean height of the robot during travel, right? We've already seen a few examples of things that didn't and did cross the gap relatively well, and a lot of them had to do with height. Things that stand up and carefully push vertically against the ground plane, those things actually tend to do pretty well in movement. That's why when you cross a sheet of ice, you tend to push down rather than just walk normally. Because when you're walking across a sheet of ice, for any given footfall, you don't know what the friction is going to be. You might actually get a firm foothold, or it might slip. So moving by pushing back or forward, unless you've got skates on, doesn't work very well on unknown terrain. Yeah? Okay. So mean height tells you something about how the robot is walking or sliding or pushing itself across a surface. F3, final orientation of the robot. As the robot moves, what is its orientation at the end? You might remember last class when we talked about my project, the Resilient Machines project, and I showed you the robot that walked in a semicircle. That kind of has something to do with how things transfer to reality. My colleagues here who wrote this paper 4 years later, they took a page out of our notebook and said that probably matters too. So they're kind of loading up B here with things, features of the behavior that are probably useful in predicting whether or not something will transfer to reality. They have a couple of them. They have 3 of them because no one feature is likely to be predictive of transferability, and we don't know how. So we have controller I, controller J. Controller I produces behavior, which produces BI, and BI contains 3 floats in it. Those 3 floating point values describe or approximate the behavior of the robot. We have controller CJ, which produces a second behavior on the simulated robot, which produces vector BJ. So we have 2 Bs now. And we can compute the behavioral distance between controller 1 and controller 2, or controller I and controller J. We can compute the behavioral distance between controller 1 and controller 2 by now taking the Euclidean distance between these 2 length 3 vectors, finally. Yeah? That Euclidean distance gives us back a single floating point value, and that's a distance metric. We're computing Euclidean distance. Distances are always positive. So the distance now between, I'm just going to talk about distance now. The distance between any 2 controllers is always a positive number, where 0 means there's absolutely no difference in the behaviors produced by those 2 controllers, at least in terms of distance traveled, mean height of the robot during travel, and final orientation of the robot. Okay, so far so good? Okay. All right, but we still need to figure out how to define the transferability of a controller before it's sent to reality. I'm sorry. So if we want to compute transferability, and again, I'm sorry about my red box here. So we've just defined behavioral distance. So now the transferability of any controller I, we can compute relatively easily by using behavioral distance. So we run controller CI in simulation, and we run controller I in reality. That produces behavior in sim, behavior in real, compute BS, features of the behavior in simulation, and BR, features of the behavior in reality, compute Euclidean distance, and we set transferability to be the negative of that. So transferability is now a value that we're trying to maximize. Higher values of transferability mean that controller is more transferable, but transferability is now always a negative number. So a transferability value of -1,000,000 means that controller failed to cross the gap. And a transferability value of 0 means that controller perfectly crossed the gap. So far, so good? Okay, so a bit of arithmetic here and simple algebra. It seems like a lot of effort for all of this. Bear with me. Okay, now we get to the fun part, which is to estimate the transferability of a controller C before we send it across the gap. Yeah? Okay, here we go. We're going to define a set of controllers, uppercase CT here. The set CT contains the set of already transferred controllers. When we start the transferability experiment, this set is null. We haven't sent any across the gap yet. When we pick one and send it across the gap and get back the behavioral features, when we get back the behavioral features of that controller in reality, we add that controller to CT, and the set CT now has just one controller in it. Every time we send a controller across the gap and get some information back, the set CT starts to grow. Yeah? Okay. So we're now considering controller C. This is a controller that's sitting in the population. Maybe that controller C caused the simulated robot to move kind of okay in simulation. We're trying to decide whether to send it across the gap or not. How do we know? If we compute the estimated transferability of that controller and estimated transferability is high, maybe we send it across the gap. How do we know? We're going to compute a sum here. Let's start down here. We'll get to the stuff on the left side of the product in a moment. We're going to sum over all the controllers in the set CT. We're considering CT, and we're going to compare CT one at a time against each controller we've already sent across the gap. Yeah? Okay. What we're going to do, we're going to sum up all of the actual transferabilities of the controllers that we've already sent across the gap. Forget about the denominator here for a moment. Let's imagine that we've sent 7 controllers across the gap already, and they've all failed. They're all terrible at crossing the gap. We're summing up a whole bunch of very negative numbers. Transferability is low, and again, forget this term. What's the estimated transferability of C? We've sent 7 controllers across the gap. They've all had terrible transferability values. The sum just says, yeah, they're all bad. We're basically just taking an average here, right? They're all bad. The transferability of C is also likely to be bad. Yeah? Generally speaking, that's kind of the intuition here. You'll notice that we're actually, when we're computing this sum, we're actually creating a weighted sum, and it's a little confusing because the weight is on the denominator here. Usually when you see a weighted sum, it's a sum of W, the weight, times the things that are being summed up. It's basically the same thing here. You can think of this as a weighted sum where this is W, this is the weight. So every time we sum up the transferability of all the controllers sent across the gap, we divide that transferability value by the behavioral distance between the controller we're considering and the controller that's already been sent across the gap. What's the intuition for this term here? What are we doing? What are they doing? Why are they weighting this sum?
The greater the distance, the behavioral distance between the two controllers, the smaller the transferability will be.
The greater the distance, so the further this already transferred controller is from the controller we're trying to estimate transferability for, the greater that distance, the more it pulls down the weight or the contribution of that controller's transferability to the weighted sum. Everybody see that? Alternatively, if a already sent controller is similar to the controller we're trying to estimate transferability for, then this value is quite close to 0, and that amplifies the contribution of C sub i's transferability to the estimate of the transferability of C. What is the intuition for this? Why are they weighting this sum in this way?
You have two controllers that are very different. What I've learned about the transferability from the one that I did put in practice, I can't apply that in theory too much.
I can't
If they're
apply it.
Similar, then you should hope that they behave similarly.
Absolutely, right? So this is sort of, the weight is like, you can think of it as what you just said, applicability. So a controller that produces behavior very different from the behavior I produce, I am controller C. CI is way over there. It shouldn't influence my estimate of my own transferability very much. But another C sub I that produces very similar behavior to the behavior I produce, I should base my estimate of how I'm going to transfer much more on the transferability of this one. If this controller is close to me behaviorally and its transferability was crappy, I should probably estimate my transferability is going to be crappy. If this one transferred well to reality, I should increase my estimate that I'm also going to transfer well. Yeah? Okay. All right. So we've got a weighted sum here, but it's still a sum. So this is a big value. We need to divide it to produce an average, not a sum. You'll notice that we're multiplying here because the weights were on the denominator. So I'll leave this as an exercise for the listener. This particular term here helps turn this whole thing into an average rather than a sum. So I, as controller C, am looking at all the other controllers that have been transferred. I look to see how close or how far they are from me, and I look at how well they all transferred, and I estimate my transferability based on that. I'm guessing that my transferability is going to be the average transferability of everything that's crossed the gap. But I'm going to modulate that average. I'm going to weight that average based on how close or how far controllers are from me. So far, so good? So now, finally, let me back up a little bit. So now, finally, we can go through all of these controllers and assign an estimated transferability to them, thanks to the fact that one of them has already crossed the gap. That set CT has one member in it. And we're going to compute the transferability for all of these. And we now have two numbers for all of these controllers. We have their behavior and we have their transferability. Which one do we send across the gap next? Some of these controllers produce more or less of the behavior we want in simulation. And some of these controllers have higher or lower estimated transferability. Which one do we send across the gap next? Maybe it helps to rephrase this. Which one do you absolutely not send across the gap next? What would be the worst choice? A controller with a high value of objective 1 and a high value of objective 2, a controller with high 1, low 2, low 1, high 2, low 1, low 2. Which one?
You definitely don't want to send something that's low and full.
Absolutely, right? Why would you send a controller that says, I produce terrible behavior on the simulated robot, and I also probably transfer poorly to reality? Actually, maybe that one you would send. If it's bad in simulation, maybe it'll be fantastic in reality. Tends not to happen. So definitely not those down here. How about controllers out here in the lower right? Controllers that have high transferability predictions, but low behavioral and simulation. The robot you're about to see costs about $20,000. If you break it, the bill is coming to you. Let's choose carefully. We don't want to transfer a whole bunch of controllers. We want to choose carefully what we send to reality. Not clear? Let me try and rephrase my question again. Okay, we've got n minus 1 controllers in the population that are untested yet. They haven't been sent to reality. We get to pick one. Is there, among that set of n1, is there likely to be one and only one that's clearly the best one to send to reality? Okay, good. You're all starting to absorb the Pareto way of thinking about things. When you go house hunting, there is no one ideal house, right? There isn't a massive mansion in a good neighborhood that's going for a song. We're going to have a Pareto front of Pareto optimal solutions. Let's see if I have a picture of this. Yeah, this will work, right? Let's say we've just sent this one across. We've got 1, 2, 3, 4, 5 individuals that are non-dominated. All the other ones, like this one back here, it is dominated by another controller. For example, this controller. This controller says, I'm more transferable, and I produce better behavior. So why the heck would we ever send this one? Yeah? So we have 5 to choose from at this point. Pareto dominance says none of these 5 is any better than the other, according to your 2 objectives. So knock yourself out. You can pick any of these 5 at random and send it. Definitely don't send any of these, but choose one of the non-dominated solutions and send that. Okay, so we send that one. It does a good or a bad job crossing the gap. We bring back the behavioral features produced in the physical robot from that controller. We add it to CT. We maybe evolve our controllers a little bit more against behavior and transferability. We delete the dominated solutions, make randomly modified copies of the surviving non-dominated solutions, run for a few generations, compute the Pareto front again, pick one, send it across the gap, back and forth, back and forth, back and forth. If you're watching the experiment and you're watching the physical robot go, it's running some controllers, and some of them do kind of okay, some terrible. From the outside, it looks like things are not so great because the physical robot isn't doing much. But unbeknownst to you, this horizontal axis, the algorithm, the optimizer, is getting better and better at estimating transferability. As the evolutionary algorithm is evolving controllers in simulation that produce better behavior and evolve to produce better transferability predictions, the Pareto front is marching up and to the right. And very quickly, we're going to start to see controllers now that transfer well to reality. The physical robot does crappy for 3, 4, 5, 6 controllers, and then suddenly it starts to get better. Everybody see the intuition? Okay, so we run this algorithm. And at the end of this algorithm, we get this. Oh, sorry, this is you've seen this one already. This was early on. This one is this is the controller at the end of the optimization process. The Mu algorithm says this particular controller, as you can see, produces good behavior. You want the robot to travel to the right. It's traveling to the right. And I predict this one will transfer well when we go to reality. Before we go to reality, look at these 2 controllers. What's the difference in behavior they're producing? This is a controller from very early on in evolution. This is at the end of evolution. I've seen these videos hundreds of times. I don't see a difference. The algorithm seems to think there's a difference. Let's see. Okay, just as a reminder, the controller in the top row, terrible transferability. The controller in lower left, transferred into the lower right, transfers well. Why? All right, this is the very last slide we're going to see in our section on the reality gap. It's intentional. This is a reminder to mind the gap. Whatever this gap is, it is subtle, it's dangerous, it pops up from time to time in unexpected ways. As far as we know, there's no good a priori way to guarantee that something that works in simulation is going to transfer well to reality. So Amazon sends you an email and says, guess what? We're now delivering packages right to your doorstep with a drone. It's about this big, and the rotors turn at this many beats per minute. Delete that email. No one yet knows how to guarantee that a machine that's going to come into very close proximity with humans, hard to guarantee. Why are we starting to see autonomous cars on the road? Because certain very large companies that will remain unknown managed to get away with collecting huge amounts of real-world data before governments knew how to regulate the practice of doing so. You can cross the gap if you collect enough data, and preferably data of your machine moving quickly, very near humans. That's actually the ideal kind of data to get. That's good for your set CT of transferred controllers. Maybe in retrospect, that wasn't such a great thing for the humans. We'll see. As you all know, as a society, we're now grappling with the regulatory and ethical and moral side of all of this technical stuff. Any questions about the reality gap before we change to a completely different topic? No? Okay, all right, here we go. So far in this class, there are 59 of you at this point. You've all coded up 59 different simulators, 59 different versions of the parallel hill climber. We'll see at the end of this class about 59 or so different fitness functions and environments. Great, okay. It's taken all of you or all of us a huge amount of collective effort, and it will have taken us 14 weeks to get there. It's not very scalable. We would like to have fewer and fewer humans producing more and more useful and autonomous and safe machines. So how do we tackle the problem of scalability, right? Robotics, mostly at the moment, is still an artisanal effort. We have very highly skilled workers that build a few machines. Some of those, like Roombas and a few drones, are mass-produced, but still very difficult to take the human out of the equation. Lots of different ways we might go about trying to scale up the automated design and automated manufacture of robots. We've seen a few partial attempts at this problem. How does Mother Nature solve this problem? Mother Nature creates machines which do a lot of amazing things in the real world to survive long enough to produce copies of themselves. Very, very difficult to do with robots so far, but it is certainly something that people have been thinking about for a very long time. So let's start a discussion about self-replicating machines with an economic argument. Presumably, autonomous, safe, and useful machines would be economically useful. People would buy them. People buy Roombas. I have a robot lawnmower at home now. We've got 2 acres at home. I don't want to cut 2 acres worth of grass. I shelled out a considerable sum to buy a robot lawnmower. There's economic reasons to create autonomous and safe machines. There's also moral and ethical reasons. There are a lot of jobs people do that really they would prefer not to do. They're dirty, dangerous, distant, or dull jobs. Let's do it. If we're going to create large numbers of machines, how do we do it? We've spent all the time in this class so far on the design part. How do you actually automatically design machines to do what you want? Then there's the manufacture side. So we figured this out a long time ago. One way to produce large numbers of useful things like automobiles and hammers and laptops and phones is to create this thing called a factory. We talked about this back at the beginning of the semester. This is the idea of mass production. It's great, but it only scales to a degree. A factory can only put out so many cars. If you want more cars than that factory can produce, you got to make another factory. Again, it's not how Mother Nature does it. Mother Nature makes sure that every single one of her factories, including the factories that are sitting here, can, at least in theory, produce other factories. The minute you do, in theory at least, you enter the realm of exponential growth, right? You build a big factory, it can produce these many cars. You build a bigger factory, it can produce that many more cars. That's linear growth. If you want to do better than linear growth, you want the number of machines or the number of organisms to grow exponentially, the only way to do it is make sure that those machines do the thing that you want. And by the way, they also have an additional functionality, which is the ability to self-replicate. Okay. So, as I mentioned, people have been thinking about this in relation to machines for a very long time. Arguably, the first person to really write down a nuts and bolts description of exactly how machines would do this was John von Neumann. You've heard about the von Neumann architecture. Every single personal device running in this room, your laptops, your phones, the overhead projector, these are all von Neumann. Based on von Neumann architecture. We're going to talk about von Neumann machines or von Neumann replicators. These are all shorthands for what are technically and formally known as von Neumann universal constructors. So at the time, this was a mathematical construct. Von Neumann wrote down the mathematics for a machine that would do this. What does that machine do? That machine has three necessary components. As long as any machine, any organism, or any actual machine has these three things, and these three things work, that machine can produce a copy of itself. The first part is a blueprint for itself. I put blueprint in quotation marks. This is a data structure. This is something that's written to disk. It's some sort of static representation of the machine itself. Obviously, this idea, formulated by von Neumann in the 1940s, he got this idea from the biologists. The biologists were starting to notice that there were some interesting macromolecules sitting in the very center of cells. And biologists at exactly this time were starting to hypothesize that that little stuff in the center of the cells is the blueprint of the cell itself. As we all know, they were right. A blueprint on its own, of course, is not sufficient because a blueprint doesn't do anything. So you need something that does something. You need a mechanism. What should that mechanism do? It should read the blueprint, and follow the instructions in the blueprint. Construct a machine, make another machine without the blueprint. You read the blueprint and you make the machine that's specified in the blueprint. And then finally, you need another little machine inside that sees the blueprint, copies the blueprint, and puts the copy of that new blueprint in the new hollow machine, and then turn it on and off you go, right? This is maybe not that exciting from our historical perspective because this is kind of what we're taught in high school biology, right? This is how machines do it. This was kind of a brand new idea in the 1940s. Okay, so this is what you need. When this is all working, you have the mechanism, component number 2, that constructs the machine specified by the blueprint. What does it do next? The copy machine, part 3, creates a copy of the blueprint, which is part 1. And then this copy is placed in the new machine, and the moment it's set inside, boom, it turns on and starts going. Yeah? Von Neumann mathematically went through a lot of effort to determine an actual instance of this. We can just say, yeah, there's a mechanism that looks at the blueprint and makes a copy of what it sees and copies the blueprint, but what exactly does that mean? What does this mechanism look like? He described in detail mathematically a machine that would do that. He didn't build it. He didn't have the ability in the 1940s to build it. it's horrendously complicated. It's like a Rube Goldberg machine. There's a lot of moving parts. And over the decades, folks have figured out mathematically how to build simpler von Neumann machines. Von Neumann machines that still have component 1, 2, and 3, and that still do A, B, and C, but do it with less and less machinery. The lower bound, how simple a machine can you make that still does all this stuff? Unknown. Yet another open problem for you all to tackle. Okay, so sounded nice, was done theoretically. Turns out that 2 decades later, in the late 50s, there was kind of an interesting discovery by a mathematician, Penrose, who showed that you can kind of do this with very, very simple machines. Penrose made out of wood a couple of these blocks and put them inside this wooden sleeve. And if you look very carefully at these 2 blocks, imagine that we take this wooden sleeve and we now start shaking it left and right. What's going to happen to these 2 wooden blocks?
Like they'll jostle, and the notch on one might link up and connect to the other.
If you look very carefully, the notching on these 2 sides has been woodworked or carpentered in a particular way, so that if you shake this thing back and forth, they kind of bump into one another, and then from time to time they kind of quote-unquote lock. They're not quite locked, but kind of. And then if you shake it some more, they'll tend to link up into larger and larger groupings. This is not replication. This is a quote-unquote wooden crystal. It's something that's made up of a bunch of very, very, very simple parts. But if you supply a little bit of energy, it starts to grow. Penrose, the mathematician, reported on this in Scientific American back in the late 50s. And this is the reading for today. He started here, and then he showed that with adding just a little bit of complexity to these wooden parts, you can go from growth to replication. Here we go. Let me see if I can get the sound for this. Okay, maybe I can't. Let me see if I can turn on subtitles. So this was what was known about the biology of self-replication in the late 50s. Quite a bit, actually, already at that time. So they're going to start by showing what we just saw, an artificial crystal that's capable of growth. Let me see if I can speed this up a little bit. So they have to seed the crystal. You'll notice he put a seed in, and then you get growth. He introduced a seed with a different chirality. It's facing a different direction and got a different crystal. That crystal had the same structure all the way along. This is an aperiodic crystal, meaning it's going to grow, as you'll see in a moment. But at any point along this quote-unquote crystal, it's got different shapes. And by putting in slightly different building blocks, you get multiple crystals of different lengths. They mentioned mutant genes there. They were already starting to understand mutation. They noticed how making a small change changes growth. Here's a slightly more complicated building block that only grows in one direction now. They've made a slight change to the geometry, and they've noticed that that alters growth, constrains growth. Turns out that you can try this at home. A little bit of child labor. Okay, now we've got clearly more complicated mechanisms. You can read the details in the reading for today. These mechanisms, as you're going to see in a moment, are capable of replication. So here's a 2-unit, a 3-unit, and now two units. So it grows as a crystal, but at some point during growth, there's a weakening of connections at a particular point, which is the point that leads to 2 components. If he had more of these available, if you kept going, you'd have 2 2-unit pieces, then 3 3-unit pieces, then 4 4-unit pieces. Okay, I think we'll pause the video there. So this was kind of a surprising result. I'm going to turn on the light. Even in this early date, back at the late 50s, that actually you could make machines replicate, and it didn't take that much. It takes a little bit of energy. You got to shake them back and forth, or the human is supplying some kinetic energy, and you can design them to be better or worse replicators. So this builds on von Neumann's theoretical result to show that you could do this in practice. We're going to see some robots that self-replicate in a moment, but before we do, one last pit stop in chemistry. It turns out that in chemistry, so even before you get to biology, you can also get self-replication in the following way. Imagine we have 5 different chemicals or 5 different chemical species. It doesn't really matter what they are. We're going to call them I1 through I5. Let's imagine that they catalyze themselves. They make a little bit more of themselves, but extremely slowly. When we talk about self-replication, it turns out that in nature, there's certain processes that actually can create copies of themselves naturally. It just takes them super long to do that, like hundreds or thousands or millions of years, really slowly. So these little internal cycles that you see here represent very, 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 very slow self-replication. So slow, let's just assume it doesn't even exist. Okay. Turns out that I1, if there's a presence of I1, and there's also a presence of a different chemical species, which we're going to call E1, E1 tends to interact with this, with this substance to accelerate the production of I1 and turn it into I2. Why the E? We're not going to spend a lot of time doing chemistry in this class, in this course. This is it. What do you call a chemical that speeds up the transformation of one chemical into another one?
Catalyst.
Thank you. A catalyst. And that's a catalyst, or otherwise known as an enzyme, something that speeds things up, right? So I1 will very, very, very slowly make more I1 and also turn into I2 very slowly. If you introduce some E1, this enzyme, it will catalyze the transformation of I1 into I2. I2 slowly transforms into I3. If you sprinkle some E2 in, a different enzyme, I2 will more rapidly turn into I3, and you can keep going, and you've got this long chain, which is relatively uninteresting. Turns out that if you reach in and make a slight change, for example, I should have named these differently. Let's imagine this is E5 prime, and this is a slightly different enzyme. This E5 might accelerate the transformation of I5 into I6, or a slightly different E5 might accelerate the transformation of I5 into I1. We now have what's known as, in the 70s, it was called a hypercycle for the reason that you see. We've got little cycles already, but on top of it, we have another cycle. Hypercycles, or autocatalytic sets. So you mentioned catalysis already, catalytic sets. So we have things that catalysize here, but they end up in a roundabout way catalyzing themselves. So if we put enough I1 into a beaker and we sprinkle in enough E1, E2, E3, E4, and E5 also, we'll see all that I1 quickly turning into 2, 3, 4, 5, and back into 1. And if there's enough, we'll start to see the amount of I1 inside increasing. The reason we're talking about this is there's an argument about, obviously, how life got started, the origin of life. In order for life to go, you need a von Neumann machine. You need something that produces more of itself. So did life invent self-replication? Turns out, most likely, that self-replication already existed. Sitting in little tide pools or deep underwater vents at the bottom of the Atlantic Ocean, there were complex chemical things going on, and some of those chemical things might have taken the form of autocatalytic sets or hypercycles, and you got more of that stuff. Some of those chemicals might float in and out of the hydrothermal vent, or in or out of the tide pool. Okay, some of those random changes might produce more of this autocatalytic set. Imagine that an autocatalytic set emerges spontaneously at an underwater vent or a tide pool, and whatever these chemicals do, they try and keep all of this stuff together. They don't let I5 flow out of the tide pool or away from the hydrothermal vent. Maybe some of these chemicals make a little bit of a gel, or they make a little bit of a soup where it's harder for stuff to seep out. Maybe some of this soup or gel starts to form a thin film around itself, and now you have a little bit of a spherical bubble with all of this stuff inside. Sounding familiar? Nobody knows, nobody was there to see what happens, but it's possible that self-replication came first, and then life and evolution got started on the back of these autocatalytic sets. Okay, kind of tangential to what we're talking about in this class. I think I'll start with this slide next time. You have a quiz due tonight. You're working on milestone 3. Have a great rest of your week, and I'll see you next Tuesday.